Today, solar cells are used in many areas of modern life. They provide power for satellites and spacecraft, where conventional fuel sources are impractical. They operate traffic signals and streetlights, supply electricity to homes and commercial buildings, and support large solar power stations that feed energy into national power grids. These applications all rely on the same fundamental idea demonstrated by Stoletov, that sunlight can be converted directly into electrical energy through physical interaction with matter. The importance of solar energy has increased because it offers solutions to several global challenges. Fossil fuels are limited in supply and produce pollution when burned, while sunlight is abundant and renewable. Solar cells generate electricity without releasing harmful gases during operation and reduce dependence on coal, oil, and gas. In remote areas where power lines cannot reach, solar technology provides reliable access to electricity for communication, lighting, and water systems. Future research aims to improve the efficiency of solar cells and reduce their cost by developing new materials and multi-layer designs that capture more of the sun's energy. These future technologies still rest on the same physical foundation established in the 19th century. Stoletov's experiments did not produce modern solar panels, but they revealed the principle that makes them possible. His work connected sunlight with electrical power and opened the path toward renewable energy systems that now play a vital role in the modern world. The operation of a modern solar cell can be understood by following the physical process that begins when sunlight reaches its surface. Sunlight consists of tiny packets of energy known as photons. When these photons strike the silicon material in a solar cell, they transfer their energy to electrons inside the atoms of the silicon. If the photon carries enough energy, it can free an electron from its atomic bond, allowing it to move through the material. Once released, these electrons are influenced by the internal electric field created by the p-n junction. This field forces the electrons to move in one direction, while positive charges move in the opposite direction. This separation of charge creates an electrical potential difference across the solar cell. When an external circuit is connected, electrons flow through the wire from one side of the cell to the other, producing an electric current. This current can then be used to power electrical devices or stored in batteries for later use. As long as sunlight continues to strike the solar cell, new electrons are released and guided by the internal electric field. This allows continuous generation of electricity without fuel, noise, or moving parts. The process directly applies the same physical principle that Stoletov observed in his laboratory. Light energy can be transformed into electrical energy through the movement of electrons. Stoletov's experimental device was designed to measure electrical effects, not to generate usable power. It produced very weak currents, but it confirmed that light could release electrons from a material. Later scientists searched for substances that could perform this same process more efficiently and in a controlled way. This search led to the discovery that semiconductors, especially silicon, were far better suited for this task than metals. Silicon can be modified by adding tiny amounts of other elements to create two different types of material, one with extra electrons and one with fewer electrons. When these two layers are joined together, they form what is known as a p-n junction. This junction naturally creates an internal electric field that controls the movement of electrons. When light strikes this structure, electrons are released and directed by the internal field, allowing electricity to flow continuously through an external circuit. Modern solar cells are based on this same principle. The main difference between Stoletov's apparatus and today's solar panels is the efficiency and stability of the materials used. Stoletov used metal surfaces and vacuum tubes, while modern solar cells use solid semiconductor layers that can operate for decades. Despite these technological improvements, the fundamental idea remains unchanged. Light causes electrons to move, and that movement produces electrical energy. At the core of every solar cell is the physical phenomenon that Alexandr Stoletov studied experimentally, known as the photoelectric effect. This effect occurs when light strikes a material and transfers its energy to the electrons inside that material. When the energy carried by light is sufficient, it can force electrons to leave their normal positions within the atoms of the material. As these electrons move, they create an electric current. In Stoletov's original experiments, light was directed onto a metal surface placed inside a glass tube, and the released electrons were collected by another electrode. This showed clearly that light could directly generate electricity without the use of burning fuel or mechanical motion. It proved that energy from sunlight could be converted straight into electrical energy through a natural physical process, rather than through engines or chemical reactions. This discovery was extremely important because it demonstrated that electricity could be produced without relying on coal, steam, or moving machinery. Instead, light itself became a source of electrical power. Although Stoletov worked with metals and produced only very small currents, his experiments established the scientific principle that made solar energy possible. His work transformed sunlight from a simple source of heat and illumination into a potential source of electrical energy governed by physical laws. Stoletov's work was recognized within the scientific community as an important experimental achievement. His publications were read by physicists studying light, electricity, and atomic structure. Although he did not achieve the international fame of later figures like Einstein, his research became part of the foundation of modern physics. His experiments influenced later developments in vacuum tubes, light sensors, and early photoelectric cells. These devices were used in scientific instruments and industrial systems long before modern solar panels existed. The ability to detect light electronically was crucial in early photography, astronomy, and communication technology. Stoletov's influence also extended through education. As a professor, he trained students who continued research in electromagnetism and optics. His methods, precise measurement, careful control of variables, and avoidance of unsupported speculation, became standard practice in experimental physics. Historically, Stoletov stands at the transition point between classical and modern physics. His work belongs to the era when electricity and light were being unified into a single field of study. By proving that light could produce electrical current, he helped prepare the way for quantum theory and semiconductor technology. In this sense, Stoletov's journey toward the solar cell was indirect but essential. He did not design panels or power systems, but he discovered the physical process that makes them possible. His experiments turned sunlight into a measurable electrical phenomenon, linking natural energy to human technology. From his experimental data, Stoletov formulated the first quantitative rule of the photoelectric effect. This rule, later called Stoletov's law, stated that the strength of the photoelectric current is directly proportional to the intensity of the incident light. This meant that doubling the brightness of the light would double the current produced, assuming other conditions remained the same. Such a relationship transformed the phenomenon into a predictable physical process. Stoletov also observed that the nature of the metal surface played an important role. Some metals released electrons more easily than others. This finding later influenced the choice of materials for photoelectric devices and, eventually, for solar cells. At the time, Stoletov could not fully explain why light caused electrons to leave the metal. Classical physics had difficulty accounting for this effect. Nevertheless, his law did not require a complete theory. It only required accurate measurement. In science, experimental laws often come before theoretical explanations. His work provided the experimental foundation for later theoretical advances. When Albert Einstein proposed in 1905 that light consisted of particles called photons, he relied on experimental data such as Stoletov's to support his theory. Einstein's explanation showed that light transfers energy in discrete packets, which can free electrons from metal surfaces. Stoletov's contribution, therefore, was not a technological invention but a scientific breakthrough. He did not create a commercial solar cell, but he revealed the principle that made solar energy conversion possible. By identifying a direct link between light and electric current, he opened a new field of research that later became photoelectronics. Stoletov's key experiments were conducted using a specially designed apparatus. He placed two metal electrodes inside a glass tube, from which air could be partially removed to reduce interference from gases. One electrode was exposed to light, while the other collected the electric charge released from the illuminated surface. When light struck the metal plate, electrons were emitted and traveled to the second electrode, creating a small electric current. Stoletov connected the device to a sensitive measuring instrument known as a galvanometer, which could detect even weak currents. He then varied the conditions of the experiment in a systematic way. He changed the intensity of the light. He tested different metal surfaces. He observed how the current changed with exposure time. Each measurement was carefully recorded. Instead of relying on single observations, Stoletov repeated the experiment many times to ensure consistency. This method allowed him to identify patterns rather than random fluctuations. One of his most important findings was that the electric current increased proportionally with the brightness of the light. This was a crucial step because it showed that the effect followed a rule, not chance behavior. Light was acting as a source of energy capable of producing electric flow. His apparatus was simple by modern standards, but it was advanced for its time. The ability to control light exposure and measure electrical output accurately made it possible to describe the phenomenon in scientific terms. Without such equipment, the effect would have remained a curiosity rather than a measurable process. These laboratory experiments marked the moment when the photoelectric effect became a subject of serious physics, rather than an unexplained observation. By the late 19th century, Alexandr Stoletov had already established himself as a capable physicist working in the fields of electricity and magnetism. These areas were at the center of scientific progress. Telegraph systems were spreading across countries. Electric lighting was beginning to appear in cities, and researchers were attempting to understand how electric current behaved under different conditions. Stoletov became particularly interested in how light interacts with electrical systems. Earlier experiments by other scientists had shown that light could influence electric sparks and metal surfaces, but no one had yet produced a clear, mathematical description of the effect. Stoletov saw this gap as an opportunity for serious experimental research. His motivation was not to build a practical device, but to answer a fundamental scientific question. Can light produce a measurable electric current, and if so, under what conditions? At that time, light was still explained mainly as a wave phenomenon. The idea that light might carry energy in a form that could directly release electric charge was not yet fully developed. Stoletov approached the problem with the tools of classical physics: controlled experiments, precise instruments, and repeated measurement. He also understood that previous observations had been unreliable because they lacked proper isolation of variables. Factors such as air pressure, temperature, and surface contamination could all affect results. Stoletov's training in experimental physics allowed him to design tests that minimized these errors. This focus on accuracy distinguished his work from earlier attempts. Rather than simply observing a spark or glow, he measured actual electric current produced by light. This shift from qualitative to quantitative research marked the beginning of a new phase in the study of light and electricity. Compared to his scientific career, relatively little is known about Stoletov's private life. He did marry and maintained a family life alongside his professional responsibilities. Unlike some famous scientists who lived in isolation, Stoletov balanced domestic stability with academic commitment. His personality is described in historical records as disciplined and modest. He did not seek public fame, and he rarely presented himself as an inventor in the popular sense. Instead, he viewed himself as a physicist whose duty was to uncover natural laws. This attitude shaped how he approached both work and family life. Marriage provided him with a stable personal environment. At a time when scientific research required long hours in laboratories, having a supportive household was important. There is no evidence that his personal life interfered with his scientific output. On the contrary, the regular structure of family life may have contributed to his steady productivity. Stoletov lived during an era when scientists were often also civil servants or university officials. His life followed a predictable academic rhythm: teaching, research, and publication. This consistency contrasts with the dramatic image of invention often seen in popular stories. His achievements came not from sudden inspiration, but from years of focused effort. This balance between personal responsibility and scientific dedication made Stoletov a representative figure of 19th century professional science. He was not an isolated genius working alone, but part of an institutional system that valued research and education. Stoletov became a professor and researcher during a time when Russian science was expanding. Universities were building laboratories and encouraging original research rather than simply repeating European discoveries. Stoletov played a role in this transition by producing original experimental results instead of focusing solely on theory. As a teacher, he emphasized precision, careful observation, and measurement. Students were trained not just to read textbooks, but to verify physical laws through direct experiment. This approach reflected his own scientific philosophy. Knowledge must be tested against reality. His research career focused mainly on electromagnetic phenomena and the properties of light. Before his famous photoelectric experiments, he had already published work on magnetism and electrical conductivity. These earlier studies gave him experience in building sensitive instruments and interpreting weak electrical signals, skills that were crucial when measuring the tiny currents produced by light. Stoletov's position in academia allowed him to work steadily without the pressure of commercial invention. Unlike industrial engineers, he was not required to produce machines or products. His task was to expand scientific understanding. This freedom enabled him to investigate questions that had no immediate application, but later proved to be extremely important. His work gained respect in scientific circles because it was systematic and reproducible. Other scientists could repeat his experiments and obtain similar results. This reliability made his findings trustworthy and helped integrate them into the broader framework of physics. Stoletov pursued higher education in physics at a time when the discipline was rapidly changing. The classical theories of Newton were being expanded by new discoveries in electricity, magnetism, and optics. Universities were becoming centers of modern research rather than only teaching institutions. He studied at Moscow University, one of the most important scientific centers in Russia. There, he was exposed to advanced mathematical methods and laboratory-based experimentation. His education combined theoretical physics with practical laboratory training, which was essential for the kind of work he would later perform. Stoletov did not limit himself to Russian academic traditions. Like many serious scientists of his time, he was influenced by developments in Western Europe, especially Germany, which was leading in experimental physics. European physicists such as Helmholtz and Kirchhoff were redefining how physical laws were tested and measured. Stoletov absorbed this methodological rigor and applied it in his own research. His early academic work focused on electromagnetism and optics, two fields that were gradually being connected by experimental evidence. Electricity was no longer just a curiosity. It was becoming a practical force used in communication and industry. Light, meanwhile, was being studied in terms of both wave behavior and its interaction with matter. Stoletov's education trained him not only to understand existing theories, but also to design experiments that could test new ideas. This skill would later become essential when he studied the interaction between light and metals. His academic success led to positions within the university system, where he could continue research and teaching. Alexander Grigorievich Stoletov was born in 1839 in the Russian Empire, during a period when science and engineering were beginning to transform European society. He grew up in a family that valued education and intellectual effort. His home environment encouraged discipline, study, and curiosity. From an early age, Stoletov showed an interest in how natural phenomena worked, especially light, motion, and mechanical devices. Russia in the mid-19th century was modernizing slowly compared to Western Europe. Scientific education was concentrated in a few universities, and access to laboratories was limited. For a young student interested in physics, this meant that progress required both talent and persistence. Stoletov's early schooling revealed his strong abilities in mathematics and natural sciences. Teachers recognized him as a serious and focused student rather than a casual learner. Unlike many inventors remembered for dramatic personal struggles, Stoletov's childhood appears to have been relatively stable. There are no records of major personal tragedies shaping his early years. Instead, his development was guided by steady academic growth. This stability allowed him to concentrate on education without interruption. His early interest in scientific principles would later become the foundation for his experimental work in electricity and light. Family influence also played a role in shaping his values. Stoletov learned the importance of careful work, accuracy, and responsibility. These qualities later defined his scientific method. His experiments were known for precision rather than bold speculation. This approach suited the growing culture of experimental physics, which demanded measurable results and reproducible data. The true importance of Stoletov's work lies in what followed. His experiments became the starting point of solar energy technology. Early photoelectric cells were developed using metal surfaces and vacuum tubes. Over time, scientists discovered that semiconductors such as silicon were far more efficient at converting light into electricity. This led to the creation of the first practical solar cells in the 20th century. Today, solar cells power satellites, calculators, traffic lights, homes, and entire power stations. They reduce dependence on fossil fuels and help limit carbon emissions. What began as a laboratory experiment with metal plates and light became a global energy solution. Stoletov's success was not a commercial invention, but a scientific success. He transformed a curious observation into a law of physics. That law allowed later engineers to design devices based on predictable behavior rather than trial and error. In this sense, he did not merely contribute to solar energy, he made it scientifically possible. His work also demonstrated a powerful lesson in science. Progress does not always come from building machines. Sometimes it comes from understanding nature more deeply. By proving that light could directly create an electric current, Stoletov helped change how scientists viewed energy itself. The need for solar cells today, clean energy, sustainability, and independence from limited resources, mirrors the concerns of Stoletov's era in a new form. His research stands as an early answer to a problem humanity continues to face: how to use the sun not just for warmth and light, but as a reliable source of power. Stoletov's most important contribution was his experimental study of what later became known as the photoelectric effect. This effect occurs when light strikes a metal surface and causes electrons to be emitted, creating an electric current. Stoletov constructed a device consisting of two metal electrodes inside a glass tube. One electrode was exposed to light, and the other collected the emitted electrons. This setup allowed him to measure the resulting electric current accurately. Through repeated experiments, Stoletov discovered a clear relationship. The electric current increased directly with the intensity of light. This became known as Stoletov's law, the first quantitative law of the photoelectric effect. It showed that light was not merely heating the metal, but actively releasing electric charge from it. This finding was revolutionary because it proved that light could be converted into electrical energy without mechanical motion or combustion. No steam engine was needed. No fuel was burned. Instead, energy was transferred directly from light to electrons. Although Stoletov did not invent the modern silicon solar panel, his experiments provided the scientific foundation for it. His work demonstrated that light could drive an electrical process in a predictable and measurable way. Without this understanding, later inventions would have been impossible. Years later, Albert Einstein would explain the photoelectric effect theoretically using quantum physics, showing that light behaves as particles called photons. Einstein's explanation won him the Nobel Prize in 1921, but it was Stoletov's earlier experiments that supplied the essential data, proving the phenomenon was real and measurable. Long before Stoletov's work, scientists had noticed strange interactions between light and metals. In 1839, French physicist Alexandre Edmond Becquerel observed that light could create an electric effect in certain chemical solutions. This was one of the earliest hints that light might influence electrical behavior. Later, Heinrich Hertz, famous for discovering radio waves, observed in the 1880s that ultraviolet light made electric sparks jump more easily between metal electrodes. These observations were important, but they were incomplete. They showed that light could affect electrical systems, but they did not explain how much electricity was produced or what rules govern the process. The phenomenon lacked precise measurement and scientific laws. Without those, engineers could not turn the effect into useful technology. At that time, physics was shifting from descriptive observation to quantitative science. Scientists wanted equations, graphs, and predictable results. It was no longer enough to say, light causes an effect. They needed to know, how strong is the current? How does it depend on light intensity? What materials work best? This is where Alexandr Stoletov's work became critical. He did not simply observe the photoelectric effect. He studied it systematically. He designed experiments to measure electric current produced when light struck metal surfaces under controlled conditions. By doing so, he turned a mysterious phenomenon into something that could be analyzed, compared, and repeated. During the 19th century, the world was entering the age of industry. Factories were spreading across Europe and Russia, railways were expanding, and cities were growing rapidly. All of this progress depended almost entirely on coal, wood, and steam power. These sources of energy were powerful, but they came with serious problems. Coal mining was dangerous and destructive to the environment. Smoke from factories darkened the skies of industrial cities, and air pollution caused widespread illness. Steam engines required constant fuel and maintenance, and their efficiency was limited by mechanical design. At the same time, scientists were becoming increasingly aware that Earth's natural resources were not infinite. Forests were shrinking, coal seams were being exhausted, and transporting fuel over long distances was costly. These realities raised an important scientific question. Could energy be obtained directly from nature without burning fuel? Sunlight was an obvious candidate. It reached every part of the Earth daily, required no mining, and produced no smoke or waste. Yet for centuries, sunlight was used only for warmth and illumination. There was no known way to transform it into electricity, which was becoming the most valuable form of energy in modern society. Electric lighting, telegraphs, and motors were spreading, and demand for electricity was growing fast. Physicists in the 1800s were already studying electricity and magnetism, but light was still considered mainly a wave that carried brightness and heat. The idea that light itself could generate electric current was still unclear. This gap between sunlight and electricity created a scientific challenge. Solving it would require new experiments and careful measurement, not speculation. This was the historical background in which Alexandr Stoletov would make his most important contribution.